Welcome to part 2 of differential equations, and this section's called separable DEs or differential equations. Have a look at up here, up at the top here, and we've got separable DEs, whatever. What are they and how do they arise? Well, maybe come over here to the right and have a look at what we've got there. They are separable differential equations, and have a look at the journey. We're going to differentiate that. Do you agree that you would get this term in here? Do you remember what sort of differentiation that's called? Remember what we're doing. If we're solving a differential equation, we're going to want to find the function whose derivative satisfies this equation. So we're going to have to undifferentiate, if you like, or integrate it, find the antiderivative. What about this one down here? If you differentiate it, do you agree you get that? Look at this in here. It's occurring in the middle there. And then when we make dy by dx a subject to the formula, you've got that expression there. So I wonder why they call them separable DEs. Can you see how they are rising for a start? Come down here and let's investigate a little bit further. Why are they called separable? Well, I think if you're going to go back and solve for the function y, whose derivative is this in both cases, I think you're going to have to separate this side a bit to get back to where y belonged in the first place, because there's no derivative that gives it just like that. That y came from the other side originally, didn't it? We might have to separate it again and reconstruct the derivative so that what? We can integrate it, because integration is the process of undifferentiating the function, of getting the antiderivative. So we've got to reconstruct the original so that we can spot what to do, if you like. So if we had this one, we know it came from this, which was, really, if we integrate this now, let's try and integrate this, we would have the integral of this, and it would be 2x squared on 2, plus now, this would be integrating that. Now, what did it come from? Increase the power by 1, divide by the new power, and then multiply by the derivative. So this has come about from the y function being a function in x, and it's actually a form of the chain rule. So this would be x squared plus y squared equals here, naught. Well, that could have been any value c. And in fact, the function was x squared plus y squared equals 4, I think. Okay, so can you see we need to get to this point so that we can integrate it, and we need to separate. So here, if you look at this one here, where did it come from? It came from this form originally. And this is, what sort of differentiation produces that? It's implicit, isn't it? It's implicit that y is a function in x, and then we multiply by the derivative. And the function was this thing, 4y squared increased power by 1 divided by new power. No need to deal with the dy by dx. That's come about from the implicit differentiation of y. Okay, and then we're going to have a constant there. Okay, so this is x cubed, take 4y squared, and I think it was 5, I think. Oops, hang on, 2y squared, isn't it? Cancel that, just don't forget to cancel that there. 2y squared equals 5. So see the idea, we've got to reconstruct the form, or a form of the derivative so that we can reverse it, if you like, get the antiderivative. So come down now and have a look. This is what we've just been doing. Let's put it back. Separate the terms. So that's why they're called separable. We don't actually recognise how to get that when there's an x and a y over on one side. So we're going to multiply both sides by y, and then we're going to integrate both sides. Okay, and we're going to say here, the integral of y, dy by dx with respect to x, is just the integral of y with respect to y. In other words, this is recognising that in implicit differentiation, you automatically create a dy by dx. And here we've got an integral of neg x, and so with respect to x, we're actually integrating both sides at this stage with respect to x. Then when we integrate them, we put 1c. There would be a c from this integration, and there'd be a c from here, wouldn't it? But let's do the two integration steps all at once and put the 1c over there. Okay, so let's integrate this. Y squared on 2, this is neg x squared on 2, and then x squared plus y squared equals some constant here. We're multiplying both sides by 2, so call the new constant k. It's really 2c if you want. So you could put 2c. But having introduced c there, when we multiply it through by 2 and rearrange, we'll have 2c. So do you get the idea that it's really very much a result of implicit differentiation? So you need to know your rules for implicit differentiation. Coming back and saying, well, when we have this down here, when we differentiate it with respect to x, it'll be 2y dy by dx. That's what we're saying. We're realising that that y must be accompanied by the derivative. It can't be separated over on the other side. So we have to separate it back, if you like. Let's put it back to where it came from. Do you get the idea? Here it is. An implicit differentiation is really a special case of the chain rule, isn't it? Where we have a function in x, let's say y squared, and y is a function in x, and when we differentiate that, we're going to do this power of y, so differentiate with respect to y, is 2y to the 1, but then y is a function in x, and there it is. So implicit differentiation is an example of the chain rule. All right, okay, so come down and let's have a look at the other one. So if you were just taking this cold and you didn't know where it came from, we must separate it. We realise that that and that belong together if we're going to detect where that dy by dx came from, if we're going to solve the differential equation. Solving it means finding an expression for y. So let's put it back together again. Separate that y term and get it back over with dy by dx, realising that that's what we're going to get on implicit differentiation. So we're integrating both sides with respect to x. Oops, and I should have in there a dx, shouldn't I? I should have left that out. And then the integral of this with respect to x is 4y dy, with integral of 4y with respect to y, and this is 3x squared with respect to x. Okay, so just watch that there. This is the idea of applying the chain rule here. We don't need to address the dy by dx. It's come about as a derivative of the y function. Okay, so we're integrating y with respect to y. It's y squared on 2, and increasing in power by 1 here, divided by a new power, so we can handle that. So this would then cancel to 2y squared and x cubed. So putting them all on that side, I suppose here, x cubed take 2y squared and the constant on the other side. And in this going back to the original one, this was 5. Normally we just have to leave it at this and then substitute in the conditions given to us, if they are, and to evaluate the c. All right, so let's go down and see if we can make some sense of all these. What is the general form? So the general form of a separable differential equation is therefore that. And how do you notice what's going on? Well, usually we just have a function in x and we integrate with respect to x. So what's this doing here? So when we have a function in y over on that side, separated from the derivative, we know we need to get it back on the other side. So we'll multiply both sides by g of y, because this is a recognisable differentiation, or a term coming from the process of differentiation. And then we can reverse that or undifferentiate, get the antiderivative, integrate it. Okay, so that's the idea. When you've got this mixed bag over here of a function in x and a function in y, you must separate that function in y and put it back where it belongs over here. Okay, so then we can recognise that as a form that's come from differentiation. So now we will integrate with respect to y and this side with respect to x, recognising here the sort of substitution method, the chain rule has been used here. So then if the integral of little g of y is g dash y, that is g of y, big G of y, then g dash y is little g, and here that's the derivative of that one. So here when we integrate f of x, we get that. So we're going to do that sort of process. And the important thing is to separate that function in y, g of y, to put it back with the y by the x, from whence it came. Same concept. Can you identify what rule has been done to produce that function? Then we're going to reverse it. Okay, so it's just another step along the same line, and here's some slope fields, and we're going to look at slope fields here for separable differential equations. So here's a separable differential equation here, and we'll integrate that. Shall we integrate that now? So, y is over that side, that's no good. Dividing both sides by y, we will have this, and then we can integrate both sides here with respect to x. It's good to put the whole thing in. Integral with respect to x. We recognise this form. It's integral, it's come from the chain rule. So integral of 1 on y dy equals the integral of 2 with respect to x. Integrating 1 on, or reciprocal function, is ln mod y equals 2x, and just put one constant of integration, combining the two constants of integration coming from those two steps. ln mod y. Okay, so y now, ln, that means the log of modulus of y is this. Therefore, y equals, that's a power, isn't it? If log is 2x plus c, it means it's a power of e to x plus c. And it's plus or minus. Now you must put that in, because you've got the modulus. It's saying that you can only find the log of a positive number. So here, y could have been positive or negative, and you took the modulus of it. Okay, so here this then would imply y equals that, which you could say now, this is plus or minus e to the 2x by e to the c. So let's say here, put the plus or minus, but this would be a constant, and call it something like a e to the 2x. Okay, so the plus or minus, this is a constant, is a. So here we put a equals plus or minus e to the c. That sort of idea there. So you've got that value out the front. Okay, so this is an exponential expression here. Exponential function is the solution to our differential equation. And you could check this, differentiate that, and make sure you came back to this function here. Okay, remembering that here your y is this thing here. All right, so you might check that, and let's try and draw the slope field for it. And we don't know where to start here. That a is combining our constant there. We haven't got an actual starting point, so we're going to have to choose a starting point on our slope field over here. So let's choose just 1 there. So what would that mean? When x is 0, y would be 1, so a would be 1 in that situation, wouldn't it? Do you get that? Okay, well, first of all, let's look at how the slope field's constructed. This time, look over here, the slope is 2 times the y value. So here, the y value is 1, so the slope here is pretty steep, it's 2. And it's 2 whenever y is 1. So here, sorry, I shouldn't have gone down there, I should have gone across here, shouldn't I? When y is 1, it's all through here. The slopes now that way have to all match up, because the slope is dependent upon y. It's 2 times y. So they're all 2's. And if I went up to 2 here, the slope would be across here, that'd all be 4's. 2 times 4. So our slope field's sort of going the other way, if you like. Doesn't make any difference to the idea. Let's try and draw this one in now, going through 1. So we're starting here at 1, it's got to look like that. We'll go up here first. So if we go here, we've got to go here, picking up those lines, those slope lines here, picking them up, getting steeper. Probably just miss that one and go up there. And down here, we've got to come through here parallel to that one and that one, and that one, and then of course it's zeroing in there to that asymptote, okay, as we would expect. We might just have a look at that. That's a little bit cockeyed there. Okay, you get the idea. It's a little bit different, but pretty similar to the slope fields we were doing before. Come down, let's do another one. dy by dx equals y. So here, where we have 1, the slope is, y is 1 here, so the slope is 1. So all through there, the slopes of the tangents are 1. Just remember this. dy by dx equals y means the slope of the tangent equals the y value at any point. So let's take the point up here, 4. Here's a point with y is 4 across here. So the slope is going to be equal to the y value, so it's going to be steep. Get the idea what the slope field is doing, putting little pieces of tangents all over the plane, but the tangents obey this rule. dy by dx, the differential equation, is equal to y. The slope of the tangent is y. Okay, do we want to have a look at that one? dy by dx equals y. We have to separate it. We've got to get that back with the dy by dx, because dy by dx came from that. So here, if we divide both sides by y, we get 1 on y dy by dx equals 1. So then we can integrate it, 1 on y dy by dx with respect to x, and integrating the other side with respect to x. Now we can see this is the chain rule has been applied here. So it's 1 on y with respect to y, integral of 1 with respect to x. So this implies that log of that equals the integral of this is x, and adding the two constants together on the one side. So here we have y is going to be plus or minus e to the x plus c again. If the log is this, that is the power of e, isn't it? The log of a number is the power. So here y equals, let's call it again, a e to the x, where a equals plus or minus e to the c. Okay, that idea. All right, got it? So you could differentiate that back and show that it satisfies that equation back there. All right, so let's try and plot it now. Where should we go? Shall we go through 0, 2 up here? Or you can try a few different ones. So 0, 2, the slope here at 2 is 2, so it looks like this. And then it's going to come in here like this. Okay, and getting steeper up there as we go, and down here like this, coming through probably about there, and it's going to go to that asymptote again. Okay, so that's the idea here, and what you can do now is just practice some of these. I've got some of these down the bottom here, so come down and have a go, and it might be a good idea to pause the presentation and have a go as you go through there. So dy by dx equals neg y, so let's do it over here. dy by dx equals neg y. Here, separating it first of all, so dividing both sides by y, we have this, and therefore over here we'll have neg 1. Okay, dividing both sides by y implies the integral of 1 on y dy by dx, integrating with respect to x, with the integral of neg 1 with respect to x, which is, we better put in the next step, integral of 1 on y to y equal to integral neg 1 dx. Don't integrate either side, do them separately, do them together and put the one constant of integration on the other side. So this is neg x plus c, very similar to the last one, and this implies that y equals plus or minus e to the neg x plus c, which is y equals a e to the neg x, where a equals plus or minus e to the c, a constant. Okay, so this is e to the neg x. Oh, we can see that here, can't we? I think it's coming down as x increases. 1 on e to the x is a decreasing function, if you like. So we could draw that in. You could draw some from up here, from down here, if you like, I don't know, you're probably more conversant with the e to the neg x, so in the positive realm, you'll see it as a decreasing function, just get rid of that. So here we get, let's say here through 1, we would have this function up here, going up, and we've got to follow the lines here, going up there and coming down here. This time, a bit hard to draw on the screen here, coming down this way. Okay, so it's an asymptote. So that's e to the neg x, it's a decreasing function. And of course you could draw some up this way here, okay, coming up here, coming up here, and this is e to the neg x for the value starting down there, and we would come, I can't touch that, and come through there. So you could draw it for anywhere there. Just remember, don't cut across the field lines, you've got to stay parallel to them, okay? So there are many different functions, of course, obviously depending upon the value of a. If a is negative, you're going to be down in this realm down here, for example, okay? So that's important to realise what's going on there. There's a whole family of functions. All right, come down and let's do another one. We've got some here for you. You might pause it and have a go. It looks a bit like a circle, this one, doesn't it? And that's what we did before. dy by dx equals neg x over y. Separate a y, put it back where it came from, multiply both sides by y. And so now we have a recognisable derivative there. So let's integrate it, and with respect to x. And then this is integral of neg x with respect to x, and therefore this implies this is integral of y with respect to y, integral of neg x with respect to x. Now let's integrate both sides. So this is y squared on 2, and we'll put its c over on the other side, neg x squared on 2 plus c, and multiplying both sides by 2 perhaps, y squared equals neg x squared plus 2c, or adding x squared to both sides, x squared plus y squared equals 2c, or we could just use k, okay, with that doubling of c, just use that, where k is a constant. So yes, that's a circle, isn't it? Centre 0, 0, and radius equal to root k. Okay, and that's what agrees over here, doesn't it? So where might we start? Well, let's start somewhere like neg 2.5 in there. So there we have it there, and then we've got to follow this around. I might be deviating a little there. Hang on, let's just have a look. Come through here, and up and up. A bit shaky, this circle. We're coming up and up, going up through here. Don't cut across them, and through and through and through. Don't cut across them, and down here, through, and hard to draw a circle here. So we're coming, oops, that's not good there. We're coming around and down. Okay, lost it in this part here. Let's go, here we go. Coming through, go this way, and we link up there. The circle's fairly hard to draw. You could check, they should all have the same radius, so this should all be 2.5. Not bad, a little bit out. But it's a bit of approximations that don't cross the tangent lines or the slope field lines, because they are tangents, they're little tangents, and tangents can't be crossed, they touch. Tangents touch the circle, or the slope, or the curve, if it's just any function. Okay, so here we have another one. dy by dx equals x over y. Same idea, of course. So let's watch it again. When you have a mixed bag of x's and y's here, it has to be separated, multiplying both sides by y. You get this, and you get x there, and then you can say the integral of both sides with respect to x is this, and then you recognise this as the integral of y with respect to y. It's the reversal of the chain rule. then integrating y squared on 2 equals x squared on 2 plus c, and then we have multiplying both sides by 2, y squared equals x squared plus 2c, or we could do it differently here. We'll put rearranging x squared take y squared equals some constant k or 2c, whatever. So here, this is actually the formula for a rectangular hyperbola. Okay, so let's have a look at that. We can do it in various ways. Why don't we put it through 1 here this time? So at 1 it's going up there, but then it's got to follow through here, and you can see it's going to be asymptotic, okay, to the line y is equal to x, it looks like, doesn't it? And here you don't know this function, but you don't have to know this function, and so it looks like that. So it's got several different forms. So the asymptotes are actually through here, as you can see, and here. So you're going to get different loads of the function in these regions. Okay, get the idea? Bit of fun, isn't it? It's a bit of a puzzle. Okay, let's go down to a couple of others. And I'm not going to integrate these too hard at this stage, but we can still draw in the slope fields, or draw in the function that satisfies this differential equation, which is represented this time by a slope field, and what we'll produce here is just the graph as the solution. So let's try and do one. Where can we go this time? So we'll go through 1 up here again. So if we start with 1, it's like this, and it's coming up like this, and it's got to go up there. Okay, and then down here, where are we going? We've got to be parallel to that one. Then coming through here, parallel, and up here, can't cross that, got to be parallel, so we're coming to the asymptote there. Okay, so we're going this way, depending on what the question says, how far to go. Okay, so we mustn't cross the slope lines there at any point. All right, let's do another one. And here's our slope field expression, or our differential equation describing the behaviour of the tangents. Remember, dy by dx is the slope of the tangent, and these tangents all follow this pattern here. So let's look at the graphical solution. Shall we go down to something like -1/2? Shall we go there? And if we go there, start there with the particular solution, we come up here and we quickly go into the asymptote, not touching that, and then coming this way, we've got to come there, flattening, and here, coming up here, and getting steeper. Okay, so we've got to go parallel there to those. Hang on, we just got to get across here a little bit. Parallel, and then to our asymptote. Now, a bit wonky in the middle there. A bit hard on the slippery screen here. Okay, so we go like that. All right, so again, asymptotes. Let's go up here. Asymptote is going to be about there somewhere. Okay, getting steeper and steeper. It's actually not asymptotic, this one. Just getting steeper and steeper up that way. All right, so here, what do you think? Are you getting the hang of this? Okay, remember you must start with whatever the question says with a designated point, and then don't cross the slope lines. Okay, come down and let's do some work with these sorts of equations. Find the general solution of the following separable differential equations. The derivative is k times y. I think we've done this one to death already, back with the slope fields. So what we're going to do, remember y dash means dy by dx, separate it, 1 on y dy by dx equals k, and therefore putting in with respect to x, and therefore that becomes with respect to y, use reversal of the chain rule, ln mod y. We've done this in the other subjects, kx plus c. Here, integrating k is kx, and the c is a constant, and here we have a as a constant. I like to put a equals plus or minus e to the c, that thing out the front. But it's pretty obvious there, isn't it? So can you see what the exponential function is? When you differentiate this, you get a k times the original function. Here, so the derivative of the exponential function is proportional to itself. It's k times itself. Maybe we should just check this. Let's just check the derivative here and see what you come up with. Y equals ae to the kx. The derivative, the constant out the front, derivative of e to the kx is itself, but then there's another function up the top here, so it's times k. So then we'll put k out the front, bracket. Oh, look, there it is. Okay, so it's k times its original y. And why does that happen? Can you see why that happens? It's because the derivative of e is itself, and you've just got the derivative of that power, the kx, times it. So that's an important property of exponential functions. What about this one over here now? They're suggesting let's get this as y take, so it's a positive y term. It's not a bad trick. So take out a negative out the front, call it neg k, y take a, and then you know this doesn't belong over there. Get it back with its mate, with a derivative. The derivative came as differentiating the y as an implicit function in x. So put it back together, set up the integral with respect to x, which becomes here, oh, this is naughty, that's wrong. This is with respect to y, isn't it? Okay, so just watch that there. That should be 1 on y take a by with respect to y, using reversal of the chain rule. So this is ln mod y take a is neg kx and the two constants together on that side. So therefore y take a this time is, or modulus of that is e to the neg kx plus c. Therefore don't forget this plus or minus. If you're taking the modulus of something, that means a positive and a negative case. And you're taking the modulus of it so you can apply the log function. Log function is only defined for a domain of positive values. So put those back in, and you've got that, so call it a b now, because you're going to add a across from the other side. So this is a y translation of the exponential function, isn't it? B is a constant, putting it there. And the constant you could put, that is b equals plus or minus e to the c, just making it a bit neater. Are you getting the hang of this now? It's very important you put that y function back with its derivative, because that's how that derivative arose, and we have to recognise the rule of differentiation that gave the original differential equation. Okay, so here we are, dv by t is that, and we're given some conditions here, so we will be able to evaluate the constant there. So let's have a look. dv by dh is k root v, so this won't do. V, the derivative of v is over there, its mate is over here, so separate it, dividing through by root v is k. And so what have we got now? We've got the integral of v to the neg a half, its derivative with respect to h, and with respect to h here. Just look at the variable given, dh by dh with respect to h. So that's our variable. So this becomes the integral of v to the neg half with respect to v, and integral of k with respect to h. Okay, so increase the power by 1, neg a half, let's check it, plus 1 is a half, I nearly wrote the answer. Increase the power by 1 is a half, divided by new power, so that inverts and multiplies, becomes 2 root v, is kh plus c. Now we can evaluate this, so we can say here at 9 for h it's 1, so we can sub that in for v, and at 13 it's 4, so subbing it in, so we've got these two because we've got a k in there and a c, so we can combine those together simultaneously using probably equimode on the calculator. Equimode, solution of simultaneous equations, or just here they're fairly straightforward. C's the same, so you could just subtract one equation from the other and you get a half, and c is neg 5 over 2. So we actually have been able to get the actual form here. So here 2 root v from up here, 2 root v is a half h, take 5 over 2, which is that. And so you can isolate root v, multiplying both sides by 2, and then square it. So that's our function. So I've been able to do a lot with that because we have been given the two pieces of information here at this line, and we can evaluate both the k that was in the original function and the constant of integration. Don't forget to check your solution. So one should then check that this will differentiate back to the original, and that it is going to satisfy that original differential equation. So you might have a go at that. All right, let's have a look now at doing some. So here are some clippings here from Hayes and Harris publication. It'd be good to have that book handy by now. And I think all of these here will reinforce the idea of the exponential function having a rate of change proportional to itself. And that's an important result. Okay, so pause the presentation, have a go at 1 and 2, and the solutions are down below, but I would toggle forward to check how you're going. Don't do a whole lot and get them all wrong. All right, let's have a look at the others here. So we've got 3, 4 and 5. You want to do most of these, get your skills up. Let's have a look at the answers now. There's through to D in question 1. And E and F. We'll just come back up a bit, little E and F there. Fairly basic. What's this ln business? A and B for question 2. And C and D. E and F. And let's look at question 3. A bit of 4. Let's look at 3 for the minute. Question 4. And part B. Question 5. And that's those done. Let's have a look at some variations now along those lines. And here's another one. So dy by dx equals ky squared x. Hey, you can't have a mixture of y's over there. That belongs on the other side. So dividing both sides by y squared, we get this. Integrate both sides with respect to x. By the chain rule, this becomes integral of 1 on y squared with respect to y. Now, integrating this, we'll have to have y to the neg 2. Don't do any integration on the other side until you do them together. So you can have one constant. Increase the power by 1. Neg 2 plus 1 is neg 1. Divide by the new power. And increase power by 1, divide by new power. So here, this becomes neg 1 on y equals a half kx squared plus c. Don't forget that constant of integration, combining the two constants from the two integration steps there. Okay, so now it is minus the reciprocal of this thing here, because neg 1 on y, there it is that, so y will be neg 1 over the that expression there. Now, that's the general solution because we don't have any information to evaluate either c or k. So that's just going to be a general solution. So you have to stop there. Get the idea. I hope it's coming to you. Okay, let's have a look at this example here now. Find the particular solutions. Why can we find the particular solutions? Because we've got boundary conditions. At the boundary there of x equals 0, we have a condition. So let's have a look at the first one. It's that one. That y doesn't belong there. It would have come from differentiation, or the derivative would have come from the differentiation of y when it was next to it. 1 on y, dy by dx is a recognisable derivative. So we're going to integrate both sides. The integral of 1, this becomes integral of 1 on y dy. So here 1 on is ln mod y, increase the power by 1 divided by the new power plus c. Therefore mod y is this, alright? The log means this thing, this whole thing is the power of e, so there it is. And therefore y, we've dropped out here the plus or minus, okay, and incorporated into a. Okay, so plus or minus e to the c, I'd like to put that in there. I think that's important to show people that you know that the modulus will result in a plus or minus, then put it into a here. Now, when x equals 0, y equals e. So therefore putting e in place of y and 0 over here gives a e to the 0 or just a. Therefore it's e by e to the 1.5x squared, or you could say e to the 1. So here you'll add one more to the exponent because you've got e to the 1 times e to the 1.5x squared. So being able to find a particular solution, a unique function, because you were given the initial conditions there. Okay, so let's take this one. What doesn't fit there? This. It belongs over with the derivative, so dividing by y squared, or calling it y to the neg 2 on the other side is 6x cubed. Integrating both sides with respect to x, you recognise this chain of derivatives here, so you only have to integrate y to the neg 2 with respect to y, and 6x cubed with respect to x, increasing power by 1, neg 2 plus 1 is neg 1, dividing by the new power, increase the power of x by 1, dividing by the new power plus c. So do the integration steps both together so you have just one combined constant of integration. When x equals 0, y equals 1. So sub it in over on the left, that'll be y to the neg 1, 1 to the neg 1 is 1 over neg 1 is neg 1, and then putting in 0 for x plus c. So c is neg 1, so just come down here a little bit, and therefore we've got our function is neg 1 on y equals 3x to the 4th on 2 take 1, and you might now like to combine these together a little bit because we want to make this a little bit neater. So here, getting this expression over one denominator here, we've got 1 take 3x to the 4th. They've left out some steps here, so this would be 1 take 1.5 x to the 4th, just doing that division, and therefore inverting both sides, y is 1 on 1 take 1.5 x to the 4th. A particular solution because we were given those conditions and we could substitute it in and make that particular or unique solution. Okay, getting the hang of it. Don't get phased by the expressions. They all work out quite nicely. Here we are back to our problem we had before, which was a circle problem that's passing through a point. Check your analytic solution by plotting it over the slope field. Okay, we did this one before, but let's do it again. There we are. Now that's got to be separated. The y shouldn't belong there. This is the recognisable form, multiplying both sides by y, and then integrating both sides with respect to x. Recognition of the chain rule means we can say this is equivalent to integral of y with respect to y, and putting the negative out the front, that's a constant, neg 1. Increase the power by 1, divide by the new power. Same with x, plus constant of integration. So then rearranging y squared, multiplying both sides by 2, is neg x squared plus 2c. But when x is 1, y is root 3. So putting in y is root 3 there, and x is 1, rearranging, c is 2. So the solution is x squared plus y squared is 4. Okay. Or we can say y squared from this line equals neg x squared plus 4, and then getting x squared on the other side. So that's a circle, centre 0, 0, and radius 2, as we discussed way back. And so you should make sure these go through 2. If you recognise the function, you should use that. And then just make sure you don't go over any slope field lines or little tangents drawn there. Okay, come down and it's your turn, and we'll finish off there. So here's some questions, question 1 to 4. Solutions are down below. Just check your work with technology. Okay, so you have a look at the graph of it and see what you think. And of course here, you should be able to display the values of the derivative using technology. So you can put derivative on under options, under the menu, derivative on in the Casio, and actually find the slope of the graph at any point. Okay, so have a look at the graph of that and see how you go. Let's go down to question 5, 6 and 7. Okay, and we'll look at the solutions now. Okay, A, B there, coming down to C, D in question 1, and question 2, coming down to, oops, hang on, jumped too far, question 3, and question 4, and question 5, and I think 6 is our last little dude here. Question 6, no, question 7 we've got. And there's question 7. Okay. All right, so question 7, make sure you understand that one. That's important. All right, well, I hope you're building up some skills. We've got more for you, a couple more presentations on the solution of differential equations. But for now, it's cheers from me.